Yeah, welcome. Just give you a little bit of background. Up until basically a year ago, I was an experimental physicist working in Halls ANC. So that's really my background. But I've always been very interested in scientific computing. I've always interfaced a lot with the IT group, network group, and data acquisition. That was sort of my niche when I was working in the halls. About a year ago, I jumped ship in a way and moved to the computer science division. So hence, I think why I got hit up for this talk here. A little bit of short notice for me, so I'm going to apologize to some degree in advance that this will look like a bit of a mix mash of two talks, because it is. I hope it will still be interesting. What I wanted to do for you today is talk about, I know many of you work at JLab, but not everybody. So for those who don't immediately work at JLab or do research directly at JLab or with JLab resources, some of this will be a little specific, although I guarantee you that no matter what you do, what facility you are at, there will be similar issues, similar things there. So look for the underlying rationale behind what I'm discussing when it comes to scientific computing, because that will exist at whatever institute you're at, whatever lab you're at now, in the future, and forever. And then I wanted to talk about some future trends. We just finished running a very large computing and high energy nuclear physics workshop at the beginning of this month. And that gave me some interesting insights into what the rest of the community is doing, for the folks that are 100% focused on scientific computing. What are the needs of the now, both in the high energy realm at CERN and at other much larger laboratories than JLab? What will we need for the EIC, electron ion collider, for our community in the future? And how are we going to get there? How are we going to serve those needs? So the very first thing I'm going to tell you, in the vein of trying to give you some practical information, is I know it's total pain often working at the lab, particularly over COVID, and if you're working remotely. So there's a few tricks and tips and tricks I just wanted to highlight that others have found useful, that I find indispensable. So at JLab, our web search, as if you've ever tried to find anything within our web, yeah, it's not great. So working on it, trying really hard. FYI, sort of a public service announcement, a lot of new stuff is going into the ServiceNow portal. Yeah, it's like, okay, but at least it's new and it's current and it's up to date. Everything that's underlined here is a link. You can download my talks when I give them to the appropriate person, and you can take a look at it. If you go to the scicomp.jlab.org webpage and you go down on the left sidebar under documentation, there's links to these guys here. So all of these are being updated. The information there is actually current. I know, shock, but it actually is true. Up until basically this week, that had all been hidden behind like non-Google indexable nonsense. But that's actually happening now. So stuff should be showing up. If you like Google JLab iFarm, for example, you actually get useful hits instead of stuff from 2013 or 2008. So that's a plus. Now, one of the things that I like to do here is this bit. So I don't know if people are familiar with this or not. This works in Firefox. Other browsers have similar things. You can give a directive like this, site : and then a domain name, jlab.org or cern.ch, and it will constrain the hit results to that, and then you give it a keyword to search on, and it'll constrain your hits to just stuff that shows up with whatever domain you put there. So I like to make a bookmark that does this, and you can follow the instructions here. And for me, if I want to search within the JLab space in my browser, I just type Control-L or Command-L if you're on a Mac, type JJ, my little keyword, and whatever it is I'm searching for, and I will only get hits from within the JLab domain. Super useful. It actually gives me useful, it's awesome. Try it. One of the other great things that you can do is for root. Who's ever tried searching in Google for root and whatever? Yeah, it turns out root is a very common keyword, right? If you do this kind of trick where you constrain it to look within the cern.ch domain, you'll actually get useful results. So good stuff. You can do it with Stack Overflow, with logbooks. It's a really useful tool. So working from offsite, if you've ever had to run root or run something that is not running within your web browser. You can SSH in and it does X11 forwarding and that's all cool, but oh my God, you click on a menu or you wait for a histogram to update and it's painful. So how many people here are familiar with VNC, virtual network computing? Yeah, okay. If you work from offsite in any context, this is a thing that you should do. Instructions can be found here, but basically the way it works is you run a server, a VNC server, as you on an account at JLab, like on JLab L123, whatever, one of the common compute terminals that you're going to SSH into. And then you connect to that with a VNC client that runs on your desktop, your laptop, whatever. And it brings up in a window everything like a full, Unix, workstation, Windows, the whole deal. It's very fast, very responsive. You can click on Windows. You can do whatever the heck you want. You can disconnect, close your laptop, go, come back, reopen, reconnect, and it's right where it left off. So you can leave things running. You can leave things up, maintain state. Super awesome. You can do similar things with something called a virtual desktop environment. JLab is working on or has this facility called VDI, infrastructure, VDE, VDI, whatever. It's a little bit easier to set up than VNC. It gives you functionally the same kind of thing. So you can give it a shot. It'll work for many of you. If it doesn't work for you and you're working in one of the halls, talk to your compute coordinator or drop me an email and we can get you set up. There's some extra permissions if you want to get on special hosts. But it also works really well. Logins aren't as persistent, unfortunately, but very useful. A couple of other little how-tos. One of the other things that I use all the time is Screen and Tmux. These are little terminal-based tools. If you SSH into something, if you run your process inside Screen, this can be a root session, analysis session, you're running some simulation, whatever. Then you can, again, close your laptop, disconnect. If it hiccups or whatever, you can come back, bring that back up, and you've got full access to it. So for example, I use a text-based mail client for most of my stuff, do all my editing in VI or Vim. So I'll bring it up within a Screen session by default. So when I run Vim, it runs Screen Vim. That means that when I go and I'm working upstairs in my office, and then I come home and I go, oh, shoot, I didn't save. I can just reconnect to that Screen session from home and either save or just get on with my work. Super useful. It's like VNC, but for text sessions. All right. So going to lean on particularly the experimentalists, but I'm sure the same thing is true for theorists. So, you want to work on your desktop because that's easy, right? And the farm is kind of annoying. There's barriers to entry. So yeah, cool, I get it. Try not to. If you're a supervisor, try to get your people past those barriers to entry for a bunch of reasons. I'm going to try and highlight some of them. Some of them impact the supervisor directly. Some of them impact you, the students, directly. So, okay. Okay. So the critical stuff here is that if you do want to work on your desktop, fine, but these rules have to be followed, and people generally don't. So, back up your code. What does backing up your code mean? Generally speaking, these days, it means use GitHub or GitLab or something. Do commits, do them early, do them often. Get it somewhere where the big thing is, if your hard drive dies, you're not screwed. Once or twice a year, some poor student or staff comes to the help desk saying, my laptop died. My thesis is on there. 4 months of analysis is on there. Can you bring it back? And generally speaking, the answer is no. And that's bad. So, the question every one of you needs to ask yourself is if your hard drive died today, like most of you have laptops, if that laptop just shut down, gave you the blue screen equivalent, what do you do? How long would it take you to get back to where you are now? If it's a week, if it's a day, yeah, cool. Then you're in good shape. If it's a week, that's annoying, but still probably okay. In many cases, it's like a month or much longer if you've got all of your analysis and it's only on your laptop. And these things die, reliability on hard drives. I literally have a stack of 30 or 40 dead drives in my office that I've accumulated from the systems that I maintain. The failure rate is low-ish, but there's a reason why companies only offer a 3-year warranty. Is because it would cost them more money if they have a warranty longer than that. So if you're at JLab, our systems try to take that into account in a variety of ways. Archival mechanisms are baked right in, so you don't have to worry about them. If you do an RM-RF on a folder, in most circumstances, you can bring it back yourself. And if you're not sure how to do that, you can put in a help desk ticket and people will bring those files back for you. So this is very JLab specific. So I'm going to go through it quickly, /home and /group. These are all automatically backed up. They're actually snapshotted hourly. So if you're typing away and you accidentally delete a file and you realize an hour later, shoot, this file I was working on is gone, or I overwrote it. I saved from somewhere other place and blew away, a presentation I was working on. You can drop into the .snapshot directory of wherever you are. It's hidden, it's secret. If you type ls-la, you won't see it. But if you type ls, cd.snapshot, all of a sudden you see this nice timestamp list of archived stuff. So really cool. Long-term backups are on tape, that goes back years. This is more for supervisors. You want to find out what your student, your postdoc was working on in the future, or you want to go back and see what did they do, or you're trying to get a project worked on again, get some future traction. Often you have to go back to disk to pick up their code. We do this all the time in experimental physics. And sometimes we can pull it from tape if it is on a JLab server. If it's on a desktop somewhere, you're screwed. MSS is an index of what we have on tape. It stands for mass storage system. If you go and look at that, if you log into the iFarm, if that's the thing that you do, you can look at a file there and just do cat or open it in an editor. And it's not actually the file. They're really tiny little stubs that tell you stuff about the file, because it's really just a fancy lookup that is exposed as a file system. You access the files through the /cache directory, and there's a few ways to pull files off of tape into cache. Work and volatile, they're on redundant file systems, like the hardware is backed, it's fully rated, there's lots of redundancy for metadata as well as for the data itself, but they are not backed up. So you have to, if they're data that you care about, you can stage them on work or volatile, but you have to push them to somewhere permanent. It's rare that files get deleted, due to hardware failure, although it's happened, I think, once in the last 10 years where there was a serious hardware failure and we lost 20% of everything that was on work. That sucked. Generally speaking, what happens here is that somebody does a cleanup and then goes, damn it. All right. So a little more information here. So, the group is a place where analysis groups, you should put your software and like analysis metadata files. Databases can go in group or in work. Work is a little more performant for access. Large files go in volatile. You can act as a scratch space, several petabytes. So you can dump big files there, check them out. If they're good, then you do your full analysis run, and you can write them to volatile, move from volatile to tape. It's a fast operation. Home, really just like have your Firefox stuff there, and maybe if you write papers, have that in home. All right, so the JLab farm is, we've got a modest sized farm. At one point it was in the top 100 in North America. I'm not sure if it still is. We've got on the scale of 30,000 compute cores, about 6 petabytes of high performance, large file systems running a file architecture called Lustre. About 5 petabytes of what's called NFS backed, or ZFS is the file system, and it's NFS backed and mounted. This is for work, this is for cache and volatile, basically big files, smaller files. Our tape system is well over 100 petabytes now and growing very rapidly. Give you a sense of scale, these computers and the associated cooling systems to keep the computers cool are on the scale of, half a megawatt of power. It's one of the significant operational costs at JLab is just keeping the compute systems up and running and keeping them happy. So if you have ever worked on a batch file system, you'll know it is not like working on your desktop, right? Which is one of the barriers to entry. You don't just log in and then, SSH in and then run a command and go home and then come back and, magic happens and your output's there. Generally speaking, this is not strictly true, and people can ask me if they care, but strictly, there's no direct access to the farm nodes. What you do is there is the iFarm nodes, or the interactive farm nodes, which are intended to be functional equivalents to the farm node. So you log into the iFarm node, test your system, test whatever it is you want to run within the same environment that software will have access to on the farm. And then you bundle up whatever it is you want to do into a little shell script. And then you can submit that to the farm. And the farm will then basically look through a big long list of jobs that get submitted by everybody who works at JLab, and we'll portion them out to different nodes as those nodes become available, taking into account the bandwidth requirements, making sure the files, if you're working an experimentalist and you're working on files from tape, that those files are actually available and they show up in time for the job to run. So always let the system do that. Never run like jcache or jget, God help us, from within your own script. Bad plan, don't do that. We can talk about why if that is a question that we want to talk about. So you can submit these jobs using a system called Slurm, or particularly if you've got large numbers of jobs that you want to run, this program called Swift, or Swift 2, which is the newest version of Swift. The really cool thing about Swift is if you fire off like 100 or 1,000 jobs and 10% of them die for whatever reason, which happens, you don't have to go through manually and figure out which jobs died and why. Swift will track all of that, will tell you that X jobs died in a final report, and then you can just do Swift resubmit, or if it died for a good reason, like a legitimate reason, some problem with a file or whatever, you can fix it and then resubmit and just do those extra 10 jobs or 10% of the jobs in one go. So that's literally what it's designed for, is to improve your workflow so you don't have to micromanage all of these annoying job submissions. The point about the farm is that while the latency is high, you have to submit and the system has to do its thing and then submit to the farm, the throughput can be really high. There's 30,000 nodes, 1,000 of your jobs can run at one time. So if you're doing a lot of data throughput, it goes really fast. It takes about a day, 24 hours for the system to respond, and then you get 1,000 jobs running all at once. So let's see, I think I'm going to skip over this because I'm going a little long here, but basically the balance to maintain, it's not just first come, first serve on the farm. You submit it into a queue associated with some account like Hall A, B, C, D, or EIC. The theory group has got its own account. Lattice has its own little sub farm. You submit to that particular group, and the system tries to keep somebody from basically squatting on a bunch of nodes and grabbing them forever, and so it tries to maintain fairness. And the more you use, the more money comes from the Hall operations to help pay for the gear. So, nothing's comes cheap. All right. So yeah, some of the things I think I've touched on already, the farm's not your desktop. You're running 1,000 jobs, or many hundreds of jobs can run simultaneously. So you don't want them all hitting like your home directory, because that's not good. You don't want them writing this to the same, foo.output test output thing. Your file name shouldn't be the same, because when 100 of these things run all at the same time, they're all going to be overwriting the same location if you've given a rooted path. So make sure you test these things. Keep in mind that many in the back of your head, you should keep in mind that 100 or 1,000 of these jobs could kick off basically at the same time. Is that going to be okay? Already talked about that. So yeah, now just a few help things. So talk to many of these things, run your thing on iFarm 1801, 2, whatever, just SSH into iFarm, give it a shot there. One of the big things that I like to encourage people to do is you really want a single script that does everything, because what runs on the iFarm is running non-interactively. When you SSH in, you're running what's called an interactive shell. they don't necessarily initialize in the same way for good reasons. So you want to have one script that sets up your full environment, runs module add or whatever you do to set up your software environment in that script. So you just type, the script maybe with a run number or something like that, or whatever it is. And that one script should set up your entire environment and do everything you want it to do. So kind of like that. If you want to rapidly debug your farm jobs, this is a thing a lot of people aren't aware of, is that there is a debug farm track. So if you're submitting with Swift, you can add this track debug instead of track, I think it's production. And there are limitations on the debug track, but it'll run really quickly. Like you can basically fire off a job to this debug track and it'll run within 20 minutes. So you can do a short test and see if your thing is actually doing what it is supposed to do when it hits the farm. And then once it's doing the thing you want it to do, you update your script, change the track to production, and then you're off and you can submit, 1,000 jobs and you're good to go. And you know that they'll run. So yeah, other things. So scheduling the jobs, right? Farm is a shared resource. So there's a number of things in place to make sure that, one person doesn't accidentally or intentionally occupy, a huge chunk of the farm and just camp out on it so that their stuff runs really fast and nobody else can run. So there are a few things that you can do. One of the things that you want to take into account is file availability from tape. This ties into let Slurm or Swift manage your dependencies, your files, your input files and your output files. You can read the documentation on how to do that if you're not familiar with it, but never call jcache from inside your script, never call jget from inside your script. These are tools, programs that pull a file from the tape system and get them on the actual computer. And one of the reasons you don't want to do that is because for the hours that it's taking to pull that file from tape, if you have a jget inside your script, you're parked on that node doing nothing but waiting for that thing to show up. Slurm and Swift will do this in the background for you and will fire off your job on a node once that file is actually present. So you don't have to wait. So it's way better. Be mindful of your memory request. Try not to overestimate. It's easy just to go, it's like, I don't know how much memory my job's going to use, so screw it, 12 gig. You can do that, but the downside is that then when the farm system is trying to allocate onto a node only has a finite amount of memory. So if you're asking for, 100 gig, then you may have a node that's got 128 cores and 256 gig of memory, but only, 3 of your jobs, well, 2.5 of your jobs might be able to run on that as far as the farm knows. So it'll wait until basically an entire node drains if you're asking for too much memory. If you're only using a gig of that, well, if you submitted it with a gig, then it can slip that in really fast into any little gap that shows up in the farm very quickly. And all those other fools with the 100 gig allocation request are sitting there waiting, and you'll get your stuff done faster. Same thing with CPUs per core. Be mindful of what you ask for. Make sure that ask for what you can use, but don't ask for more. So, if you've got in Halls ANC, our primary analyzer, it can only use a single core, unfortunately, for reasons. So asking for more cores does nothing other than tie up nodes and takes it longer for your stuff to get scheduled. The same thing is often true for Géant simulations, depending on how you write them, what you're working on, and other stuff along those lines. So be mindful. Just ask for what you need and your jobs will run a heck of a lot faster. If you underestimate, you ask for a gig and your job requires 1.5 gig and it comes back getting killed. Okay, if you submitted it with Swift, you just say, resubmit it with a 2 gig allocation, you're good to go for whatever fraction of jobs failed, because they got a really busy track or whatever. Yeah. Okay, so there we go, yeah. Self-inflicted wounds. The other thing that I wanted to touch on, it's becoming less of a problem, basically because software is being updated, but small read-write operations can take down like an entire file system, which affects everybody at the lab. This happens every once in a while. The big offender tends to be debugging output. So you write a simulation or something, and then you do a printf to standard error, like on every event, because you're debugging this thing on your desktop and you're trying to figure out what's going on. And then you forget to turn it off and you fire off 1,000 jobs. And the thing here is that standard error is not buffered. So it basically, functionally, it opens the file, writes your one line and then closes the file. And then on the next line, it opens the file, writes one line, closes the file. When you've got 1,000 things on a really fast core doing this all at the same time, the entire life of the file system that is serving everybody is just focused on your job. And everybody else gets grumpy. So don't do this. Yeah, and this just ties into the fact that workflows and procedures that are just fine on your desktop or on your laptop may not scale well on really fast computers where you can have 1,000 of these things running across a distributed system at exactly the same time. So that's a big difference that people often don't think about until somebody from SciComp, comes knocking on your virtual door via email going, it's like, yeah, you've got a bunch of jobs that took down the farm. We're going to basically shut that off for a while until you fix it. There are tools to let you check your job status to find out, where errors are, what's going on with all of your farm jobs, to see how much memory your jobs are actually using. All that good stuff. You can go to scicomp.jlab.org and look through it. All right. Anyway, I'm going to stop there. Do you have any questions for the moment before I jump into some of what newer things? Yes.
All right, my workflow on JLab at SciComputing has always been SSH into the JLab Science Computing from remote, and then immediately SSH into the farm. Is that bad, or at least useless?
No, that's not bad. Of course, just within the last few months, right, you have to two-factor in. That's one thing I didn't go into here. I think the documentation is pretty well written, assuming you can find it. It is off the SciComp webpage. There is like the Sci login nodes. One of the things that people aren't aware of is you don't have to go to login.jlab.org and then to Sci login and then to iFarm. You can just go straight to Sci login. And for experimentalists, you can do the same trick by going to like Hall Gateway. You don't have to go through login and then the other. All of the two-factor nodes, for the most part, let you jump off it to any system. So yeah. Anyway, that was a bit of a parenthetical. Did I actually answer your question?
My question is really just whether or not there's any reason to jump into iFarm if you're not about to try to, send jobs.
The main reason I use the iFarm is that the iFarm is the only set of systems that has interactive access to like the cache file system and volatile in general. So if you want to access files off of those systems, you have to log into the iFarm node. If you're just working in group and work, then you can do everything you want from JLab, like JLab L1, JLab L2, that kind of thing.
Thank you.
Yeah.
So I know that Swift 2 has a max job or I guess, what is it? It has a max run jobs of 500. So like if you submit 1,000 or so jobs, you're only allowed to essentially run 500 of them at one time, essentially.
I think that's a limitation of the scheduler. Is that won't allow something on the scale of 5. I mean, it's a tunable number, right?
Oh, is it really?
Yeah, and one of the main reasons for that is basically to avoid. It has a number of impacts. A lot of it comes back to this fair share notion, where Hall A and C each get like 10% of the farm and et cetera. If somebody is waiting in the queue and they've got 8,000 jobs that they need to run, then they can all jump in and grab this huge fraction of the farm, which may be okay under fair share at that moment in time. And then they just park there for like 2 days and starves everybody else out. So they try and, constrain the number of concurrent jobs that can run. For that reason, the other big reason is to help mitigate potential damage if you've got a set of 500 jobs that are writing to standard error every, 10th of a millisecond.
Okay. So it's advisable to keep it at 500 then, or?
I mean, yeah, I think. So if you're running into it at the Swift layer, like you're trying to submit or generate a queue of jobs, within Swift or within Slurm, you can have it, basically run through a loop. If that's the thing that you're doing and you're getting maxed out at 500, then I just honestly, what I would do is I just write myself a script that writes it in a couple of different groups,
Oh, right.
499,
There's always a
500.
workaround. Yeah. That's right.
And then you've got, 3 or 4 different batches. However, one thing, and this is, I want to make really clear, if something is a total pain in the butt in your workflow, like if you're running into something that is just really frustrating and is driving you off the farm or making you try, jump through a bunch of hoops, like this, like potentially this kind of thing, having to segment up your jobs, personally, talk to us. Because one of 2 things will happen, and you can talk to me personally too. You send me an email at brad@jlab.org. One of my primary roles now is to act as an interface between the experimental computing side in particular, but mostly the scientific computing group and the IT group, the CNI central systems folks, to fix these pain points. So one of 2 things will happen. Either there's already a solution and it's just not well documented, or you need a little pointer to something, or it may be a legitimate thing. Like, the jobs have scaled beyond where they used to be, and we're hitting this is a new problem. And we fix it, like for you and for others too, because then it goes forward. So if you run into problems like this in your workflow, ask.
This is related to the question Andrew asked. So if I understood you correctly, to access the group and work directories, I don't need to be logged into the farm computer?
For group, for sure. If anybody wants to SSH in and remind me, I can't remember about work. I thought you could access work off of the central systems, JLab-L, but maybe those are only tied to iFarm. I'm not sure.
Okay, I wasn't
honestly.
Thanks.
But group and home for sure. Just as an aside, talking about the VNC session, which is something that I do regularly. I find it best to run a VNC server, and you can read about the terminology and the how-tos on the JLab-L whatever machine, because there I don't have to jump through the 2-factor authentication to get to it. So it's a little bit faster, a little bit simpler. And then inside that, when I connect with my VNC client, then I just open a terminal and SSH from there into the iFarm. And from there, you can do whatever you want. You can close your VNC session when it comes back up. You don't have to jump through the 2-factor hoop again, because you remain connected to the iFarm node within that VNC session. All right, so I'm going to go through pretty quickly. This is going to be a high-level overview, so I'm not getting into the weeds. My goal here is to run through a number of things that I found interesting and that I think are really what's going in the future. I'm going to touch on in terms of scientific computing, both here and at future facilities, either JLab nuclear physics related or high energy. So some of these you may have come across, some of them just keep your ears open, so to speak, and they'll be coming into play. A number of them will be coming into play here at JLab in particular. Others are just cool if you like this kind of thing. So this is a really big conference that JLab put together that ran a couple of weeks back, and it had, like I had on the previous slide, 450 different talks across a bunch of different sessions, a lot of people. And I'm just going to run through some of the highlights, some of the things that I thought interesting. Some of them tie into, and one of the nice things was that nuclear physics has always been kind of a small group within the larger, high energy physics community. It's hard to compete with SLAC and CERN. They get vastly more money than we do. And yet, a number of the things that we are doing at JLab caught them by surprise, and they thought were really cool and called them out as highlights among these 450 other talks. JLab's a relatively small lab. We only had like 12 people or something presenting at this conference. And many of our people got called out as doing really good, innovative work. So I thought that was really awesome. So I'm going to run through some of those specific things that we're doing at JLab too, that caught my attention, or just partly to advertise, all the good work JLab's doing. So, data, metadata organization. One of the things, this is kind of cool. This is a graph-generated global infrastructure of the high energy physics data analysis, right? So this is actual. This tangled web of stuff is, I have to dig it up, but it's somebody's actual data analysis workflow, is that really complicated mess. So how do you manage that kind of thing? At Jefferson Lab, we're not quite there yet, but as systems scale, We're getting there really quickly. So how do you manage that? Well, the tedious stuff that you used to do by hand, you start to automate. And this is one of the big things, one of the big themes going on is how do you automate these? What systems are available to do the automation? How do you move files around? One of the things, if you're in Halls Bravo or Delta in particular, you're probably familiar with the Open Science Grid, moving jobs. Basically you want to run a job and get your simulation or your data analysis done. You want to take advantage of a compute facility that is not the farm. How do you do that? Well, there's an infrastructure called the Open Science Grid, and there are others, Amazon, AWS, Google Cloud Services, all these other cloud-based platforms, where ideally you'd like to just, rent a computer for a bit. Open Science Grid is free at some level. You can just submit to it. But how do you move your files around? We've got literally petabytes of files here. How do you move them around? XRootD is a file transfer protocol that we're going to be using, that we are using at JLab. We're going to be using it a lot more. Ruscio is a really nice thing where it allows you to manage. It's a large frame. Well, it's a sophisticated framework that can be developed at CERN, that can be spun up anywhere. And the really interesting thing about Ruscio is that you can say, okay, for all of these files, I want to have at least 3 copies of them, of those files for redundancy purposes. One of them has to be on tape. And I've got data centers, over in Europe and another one in Canada. So I want to have some, files that are from a networking distance perspective, close to those facilities. And you can just tell Ruscio that, and then Ruscio behind the scenes will just make it happen, which is really cool. So that's one of the things that we're going to be working at, implementing here at Jefferson Lab, again, in anticipation of making it easier for people here to take advantage of these offsite compute facilities and move the data around. The other big thing is networks. The amount of data that we're moving around, that we need to move around, is increased to the point where networks are a major bottleneck. They always used to be a bit of an issue. But at the high levels, you could basically throw money at it and the problem would go away. That's no longer possible. So we need to start viewing, and this is one of the things that came up in a lot of talks, we need to start viewing network bandwidth as being a scarce resource in the same way we think about disk, CPU, or, if you're an experimentalist here at the lab, beam on target. There's only so much of it to go around, so don't waste it. And how do you use it efficiently? So there's a lot of interesting things. It has a direct impact on compute models. Where do you run your stuff? Well, is it worth it to sit and wait and just run your jobs on the farm here at JLab, and because that's where all the data is, and keep it local? Or is it more efficient to move the data off to some other place, get the results, and move it all back? Moving all that data out and back tends to be the expensive bit. Well, it's one of the very expensive bits, particularly if you're on Amazon or Google Cloud. Renting a CPU is cheap. Moving data around is really expensive. So, all these trade-offs are very interesting. Basically, we can't treat it as a black box anymore because it's integral to our workflows in a way that we used to just not think about. Streaming readout. I think I saw some slides up just previously talking about streaming readout work, maybe at the lab. Certainly it is where data acquisition is going in the long run. And not surprisingly, I'm sure you had heard of some of it, raw data rates are really big when you've got sampling front-end payload modules that are, measuring a voltage or measuring something every 4 billionths of a second, and they can take every one of those measurements across 20,000 channels and push it down a pipe somewhere. Your data rates get insane. So how do you deal with all of that? Well, there's a bunch of things. LHCb is working on some proof of principle. Alice is also doing a proof of principle measurements. It's a lot harder than it sounds. And it is not plug and play. So I know a lot of folks at JLab have plans for like level 1 farms and level 2 farms and things like this. There's reasons why we have been talking about it for 30 years and we've never actually done one. So it's hard, but it is looking like it will be a thing that we have to do going forward because the data rates are expanding faster than our ability to process those data. One of the other very interesting things is using a term that you may have heard of, heterogeneous architecture. which as far as I can tell, just means like non-Intel based CPUs. So that includes, usually when people say heterogeneous architecture, they really only mean two other things. Mostly they mean GPUs. Sometimes they mean FPGAs. Is anybody, who knows what an FPGA is? Very few. Okay, so it stands for Field Programmable Gate Array. It's basically a way of uploading firmware onto a chip and turning it into a very special purpose integrated circuit. So you get all the performance benefits of going out and constructing a silicon application specific integrated circuit. But when you inevitably screw up, you can reflash it and fix your bug without going to the foundry and having to cast a bunch more chips. So not cheap, but they can be really fast. And ARM chips, the ARM computing architecture, which is what Apple's using in their modern laptops. It's what Raspberry Pis use. It's interesting. One of the big things that we run into a lot in both online and offline computing is not, fast isn't as important as power. So we often talk about the number of compute cycles per watt, per unit of power is more important than per time, megaflops, petaflops, exaflops. Because if you don't have the money to pay for all your computing, it you may as well not be there. And turns out that ARM architecture does very well when it comes to compute power per watt. So that's one of the things that people are looking at. Containerization is huge. I'll touch on this again. A couple of interesting things. These are a couple of things that were called out based on work here at the lab. If you've been involved in Hall, Bravo, and Delta in particular, you may have run across Hydra and this AIEC. I'll touch on both of those just very briefly because I really like them. As you might imagine, I'll touch on this again. Artificial intelligence and machine learning is ubiquitous through all of this stuff. I don't know if you guys have used it in your personal work or not, but it is an incredibly powerful toolkit. It will often get you 80% of the way there very quickly and then completely screw you over for that extra 20% of detail. So be mindful of it, but it is a super powerful tool. One of the really cool things that we've done using that tool here, which is literally people were coming up, and when I first heard this, it was one of those things where you go, oh, why didn't I think of that? Because if you have, how many people here have run shifts in an experimental hall? Okay, a good number. One of the things that you need to do is you basically go and, every hour you're looking at a bunch of plots, histograms to make sure that the data look good, whatever the hell that means. It's exhausting as detectors become larger. There's more and more plots you have to look at, and it's tedious. And often you don't really know what good is and what bad is, right? Unless you've been around and know how to interpret the plots. It's just a bunch of things. And if they look even remotely close to the other thing, it's like you just get on with life. So these are just images. What is one of the things that AI has been trained against for 20 years? Image recognition. So you know what? You can take a bunch of images that are flagged good with some that are flagged bad, run an AI trained model on those images and have it figure out, or basically work out what is good and what is bad for each of the histograms that you as a human have to look at. But once it's done, the computer can do all the tedious crap. And turns out this works really well. And it's called Hydra. It's rolled out in all 4 experimental halls right now. There are challenges with it. One of the tedious things, of course, is the training, particularly in halls A and C, where the configuration changes a lot and the plots can change significantly, but remain good. They change for kinematic reasons, not because half your detector turned off or something. So one of the interesting things, and this is again coming up later, is I was saying that AI ML is incredibly powerful and it'll get you 80% of the way and then kind of screw you for the last 20%. Yeah, well, one of the ways that is a very active area of R&D throughout the nuclear physics community and high energy physics community, but just AI ML in general, is trying to work out, in this particular instance of anomaly detection, why does something look different? Like, if your neural net is firing in a way that is generating a classification of bad, why is it doing that? You've heard about the ChatGPT stuff, right? And it'll spew out some nonsense at some point. Well, it's a really complicated model. And one of the big problems with AI ML models is that it's not analytic. You can't say, oh, it's this heuristic rule over here that is failing because of a corner case. So trying to get some insight into the model, what neurons are generating, are weighting the output classification to bad is very important, because you need to have an interpretable model in science for it to be actually good. And the more complicated things get, you need to be able to debug them. So you need to have some insight to what that AI model is doing, how it is thinking, in heavy quotes, in order to decide for yourself whether it is doing what you intend it to do. And there are a lot, like I was saying, a lot of R&D is being done on this. And this is one example of that being implemented within Hydra, where this guy is getting flagged. Basically this set of detectors is being flagged as having a problem. Well, why is there a problem? And it shows this heat map. It's predominantly due to this element here. This is an obvious one that you can see by eye, but there are other examples where it's a little more subtle. And when you've got 1,000 images, it's nice to be able to have it tuned into the one that the AI is focusing on, in a sense. AIEC is another JLab-based R&D effort that has parallels across all of the other labs. The interesting thing here is that this is actually in production, whereas at other labs, they're being a little more conservative, and they're not. And as an experimentalist, I get it. But the interesting thing here is basically to have your detector learn, or rather your AI monitoring system learn from all of its inputs, what good operation looks like and what bad operation looks like. And ideally, so that's in the anomaly detection sense. In this case, it is learning based on variations in the inputs. In this case, this is a relatively simple process with just 3 inputs, basically the atmospheric pressure, gas temperature, and the high voltage, basically the power to that particular detector, were the inputs. And the AI/ML system was trained to try and figure out how these things impacted this, basically a measure of the detector efficiency. And you don't want your detector efficiency varying a lot, because if you're doing analysis, every little bit of detector efficiency is like an extra grad student month of screwing around. So one of the cool things they did is they've got this big, gas tube detector or straw tube detector. Half of it they left standard, half of it they instrumented with the AI-based system, pre-trained, and then they ran it. And you can see the blue AI-tuned system is nice and flat compared to the unmonitored, unmanaged system. And again, all of this stuff here is, computers are good to do the tedious stuff that humans used to do. AI/ML is a very powerful way of trying to automate stuff. And this is what is being done here. And as the detectors scale up, it is very difficult for one standard grad student to go through and monitor all of these things and make the adjustments on the fly and still sleep and eat. So these systems are becoming more and more important. So offline computing, another big category, of course. Just wanted to highlight here, I've talked about this a lot, machine learning is pervasive. Track reconstruction, anomaly detection, I've talked about those two already. One of the other interesting things that I was unaware of up until a year and a half, 2 years ago, are these AI/ML trained, what are called surrogate models, which is one of these things that I will admit, I'll be interested to know what your reaction is. When I first heard about this, it's like, oh, that's baloney, except I didn't say baloney. The more I thought about it, though, it's really cool. It makes total sense. So this FASM project, which is being worked on here at the lab, is using AI/ML to train a model so let's see. So let me back up. So say you've got like a Géant 4 model, or you've got a piece of software that, say, hypothetically, experimentalists will know what I mean, your supervisor handed to you that they got from their supervisor, and it's like a black box, but it's well validated, and it's definitely based on updated cross sections. But nevertheless, and God help you if you have to recompile it, because it's probably using, Fortran 60 or something. One of the cool things you can do, and not only with with old things, with well-established, very reliable software like that, is you can essentially, it's a little bit like fuzzing in a sense, but you can basically run through the parameter input space with your AI with your AI ML program and train a neural net against the output. So, the way I think about it is that essentially it's a multidimensional fitting process, right? Where you've got an input set of parameters, and then you've got an output space, and you're basically trying to map an input to an output. It's a fitting process in my mind. The interesting bit that AI ML lets you do is that the parameterization is also handed off to the computer to figure out. Historically, you'd use something like, polynomial expansion or something, right? If you're being lazy, or you might have some physics-based model that you put in for your parameterization, and then you fit, and you tune all the different parameters to match so that your input gives you the expected output. Classically. Well, AI ML, the advantage of this is that you can automate not only the fitting process functionally, but you can also automate the how do you parameterize it, which is awesome. So what you can do here is you can take your fancy, perfect, Fortran 60 code, and essentially let your AI ML software parameterize it for you so that you can feed your AI ML model a set of inputs, and you'll get the same things coming out of that AI ML model on the output. But now you can run that AI ML model on a GPU or on ARM or on some other architecture without having to recompile or re-architect that thing for that system. Anybody who's tried to rewrite code to run on a GPU will know it's not easy. It's a very different architecture. You have to think about and break the problem down in a very different way. So this is amazing. The first time I heard that, it's like, oh, that will never work. And then I started thinking about it the way I described it to you, and it's like, that probably works. And you can do this for all sorts of problems. So you'll see surrogate models for GEONT4, like for cross-section based stuff. And it's basically, in my mind, I think of it in the same way. You're letting the system do the parameterization as well as the fit. So again, we've got all the same issues that you still have with any kind of parameterized model. When you get outside of the region of your data, or what you trained on in the case of AI ML, or what you fit against in the case of a standard conventional, chi-squared minimization kind of thing, your output can flop around and do really weird things. But that's true for everything. That's always been true. And this is where, in the case of AI ML, this kind of work is very important, is to try, because it's a little more opaque in the AI ML sense. Are you hitting a domain where you're just outside of the training that you fed it? Or is it finding new physics because you haven't looked there? And, are you interpolating so it's something that's plausible, or are you extrapolating and it's just your, 28th order polynomial fit that's flopping around out at the end of your fitting space? Anyway, really cool idea. Keep an eye out for it. The fact that you can use the computer to develop software based on other software so that you can run it on new architectures like GPUs with huge performance improvements is pretty awesome. So distributed computing, another big topic, of course. I was talking about this earlier. You've got a compute resource here at the lab, 30,000 cores, while you've got the entire Amazon cloud service, you've got Google Cloud Service, you've got Seal, you've got the Open Science Grid, you've got a million other cores and data centers distributed around the world. That's where everything is going, is distributed, not just locally, but everywhere. And how do you manage that? I talked a little bit about some of the toolkits to handle your analysis workflow. Here as an example, how do you work with the farm here? Well, you use Slurm or Swift to submit a job, and then magic happens in the back end, and hopefully your data files show up in volatile or on cache, and it's all good. How do you do that if you want to submit a job here and have magic happen where those jobs can go offsite and do their thing and come back? So now you've got access to, instead of 30,000 cores, you could have access to 30 million cores. So there's a lot of central organization frameworks. Many of them were born in the high energy field, but it's amazing how many other fields, these are becoming standardized. So, Pata Dirac, Ruscio comes up again here. This is being used in the astrophysics field, the gravimetric fields, to shuffle these large data sets around, because that has become a common enough problem that while, sort of the first pain points were found within the high energy physics community at CERN, trying to move things around Europe, for example, and with partners in North America, this is now a much larger problem. And open source, thank goodness we're all running open source stuff, is basically owning the field. And with a lot of these technologies, one of the nice things is that there's consolidation and there are teams based around Ruscio. It's not just 3 grad students and some overworked postdoc trying to keep these things up and running now. There are people that are paid to work on these individual systems, which is great. Let's see here. So yeah, sustainable and collaborative software engineering. Continuous integration and build infrastructure is also great. Again, it's using computers to do some of the things that you would normally do. You're working on some code, you make a change, who hasn't gone home and then come back later and realize they borked the analyzer for their, overnight or something. It's a thing that happens. Continuous integration, if you check it in, there's a lot of systems, both on GitHub, GitLab, and elsewhere, that will basically run a set of standard compilation checks and try and make that easy for you. Does the thing compile? If it runs a standard bit of analysis, like on a small run, does it get the same output that it got before, even after you made your change? So these are things that locally, for you folks, if you're writing code, you need to be aware of and think about, would they help your workflow? And this is less if you're just a one-off person, but most projects these days are large enough that you have multiple people working on them at a time. So when you have multiple people working on them at a time, it becomes more important that you don't screw over your neighbor by committing code that's buggy or by committing code that breaks a build. This kind of stuff makes that easier, simplifies your life. One of the other cool things that I thought that was interesting is they're doing, meta-analysis, like how are people doing workflows? And actually doing, it's like research on the research that we're doing. And this is pretty fascinating. One of the things they actually did is they took every single Git repository in Atlas and started running analyses across it, looking for things like, looking for patterns. What libraries are in use? Are those libraries current? Are those libraries using known bugs? When a known bug is fixed, how long does it take for that bug that bug fix to flow through your entire build system? Kind of neat. How many people here have used Julia? Yeah, okay. This is one of these languages that I had heard of, but I have never touched. It came up a bunch of times, and now I'm really curious about it. It was presented as being really a sweet spot between the performance of, C++ or some low-level language and Python, where you've got access to a lot of the syntactic sugar and libraries to, throw a few lines down and have a thing work rather than having to, manually map in 100,000 include files and write your header and all that stuff just to do a printf. So this is cool. And I don't know if I've got the slide here or if it's coming up, but one person, it'll probably come up here somewhere, basically re-implemented their analysis process over at Atlas within Julia, and it ran 40% faster and gave the same outputs. Cool. Yeah, I won't belabor this, but there's been a lot of work on root internals, which is going to be hopefully paying off. So hopefully when we work a little bit better at standardizing our workflows here at JLab, these kinds of improvements will just automatically flow down to you as a user. But keep in mind that newer versions of root, one of the nice things that they've done is they're really working hard to multi-thread the internals. This is a challenging thing for any of you who've done multi-threaded programming. Making thread safe statics is a real issue, but there's been a huge amount of progress on this within root that allows you to basically take your software, developed around root and, throw it on any kind of a modern architecture that has multiple cores and actually be able to take advantage of, 32 or 64 or 128 cores all at once without weirdness happening. Getting close to the end here, facilities and virtualization. This is going to reiterate, a lot of things that I've already mentioned, but containers are everywhere. How many people here have used containers? How many people here know what containers are in this context? Maybe a third. How many people have used them? Yeah, okay. So that's a problem, not for you people, for us. This is something that I've been trying to lean on and trying to build up the infrastructure here at the lab to make using containers easy. So for those of you who aren't familiar with it, containers are a way of packaging a software environment in kind of a self-contained unit so that you can run it essentially anywhere. That's not quite true, but to a large extent it is. So one of the problems that you may have run into is, you're working on software on your desktop and you want to run that same software, so you've debugged your stuff and of course you're checking it into Git because you're good scientific citizens. And now you want to run it on the farm against 1,000 jobs or something like that instead of the one root file you downloaded manually to your laptop. And then you go to JLab and, it's a different version of root and it's a different version of this and the compiler isn't available and, it's just a nightmare. And then you say, screw it, I don't want to work on the farm. I'm going to do it all on my desktop. Containers are one of the ways around that. You could package up and build a container on your desktop and then run that container within the most common framework that we use here is, well, it was Singularity that's since been renamed Aptainer. They're the same thing. Singularity is going away and it's being called Aptainer now, but it's really just a rebranding. And it should just run. If you built your container properly, then you can just run it. You can move it from your Linux desktop to your Mac, more or less, to Windows if you are a sucker for pain, and it'll just run. The other awesome thing about containers is that you've got a working environment analysis process, and it's sort of working at a certain point. You can snapshot that and put it somewhere, keep working. And then if you want to go back and you say, okay, here's this thing that we understood, it looked good, at least within the domain that we were exploring. I've rewritten a bunch of stuff, rewritten my software, taking advantage of an AI ML surrogate, who the hell knows? Does it give the same answer? You don't have to 3 years later go back and try and recompile the old software. You can run that container again, in the news with a new input, for example, that maybe is relevant to your new software. Does it give the same answer? This one might be, 100 times slower if you've re-implemented things to use GPUs over here, but you can directly check the output. You basically snapshotted your runtime environment. Super useful. It also lets you do these other great things where you can push these containers out to Amazon or out to Google or out to Open Science Grid. Because it's a way of encapsulating your local software environment. Very good stuff. And we're trying to work hard on making that easier to use here at JLab. It's more challenging than it should be. Yeah, one of the other things, just a couple more slides. So one of the other very interesting things is, I was talking earlier about networks and how they had to be, they're core to what we're doing right now, right? They need to be fast, they need to be reliable. You throw a packet over the fence, it better show up on the other side. Or if you're doing streaming readout, you turn off your DAQ for a while and everybody gets really grumpy really fast. So how do you do that? Because as these systems, if you're having to transfer data in a streaming readout environment, like at the EIC, for example, from your detector, and you want to fan that out and analyze it across a distributed, like a globally distributed network, you can't have part of that network just shut down. And then what do? Shut off your, $10,000 or $50,000 an hour beam because you can no longer handle the traffic? That's no good. Can you quickly go and, reconfigure the router at 2 a.m.? Not very fast. The complicated system is complicated. So again, following a theme, let's try and figure out how to get the computers to do that. And this is one of the EdgeFat and IRIAD, we'll read the acronyms, are two projects that are being developed here at JLab that also got called out as being very interesting within a larger community. These are ways of using AI ML to both model a system so that you can do basically anomaly tracking within an AI ML model. Like, so if you're tracking inputs from your farm nodes, anything from temperatures to CPU concurrency to cache hits, whatever, lots of, data flows, that kind of thing. If something starts screwing up, there may be precursors that if you were staring at it, you might notice, but you can't stare at it because you need to sleep. You can have the computer look at it, very much like Hydra, and watch for these kinds of things if they're trained. And then the interesting bit, there's a whole bunch of interesting bits, actually. So one of the interesting things here is to sort of rethink how we get data from point A to point B. I don't want to get into the details too much, but right now, essentially, you've got a starting point and an end point, and they're fixed. So they're uniquely identified. You can do a little bit of trickery to do some failover or something on one end. But it's destination, it's source to destination, not based on the thing that you're sending. Like, it's not based on the data that you're sending. For example, if you've got a bunch of detectors and you've got a portion of your infrastructure devoted to cluster finding, from a tracking detector environment, and you want to find clusters, and then those clusters get sent over to a tracking detector, which draws lines between them to actually get, tracks and identify particle momentum, whatever you want. It would be really interesting if you could flag those data as saying these are data that have to get to a clustering system, and just throw it over the fence and let the underlying architecture make sure that those data get to the cluster finding system. Having that ambiguity, that ABI layer, that breakpoint where it doesn't have to be that particular computer in that rack, in that node, but it just needs to get to a cluster finding system, allows the architecture to figure out, okay, right now I'm using these computers in these racks, they're configured to accept those data and generate track information, which they will then throw back over the fence to the tracking stuff. So if, the track reconstruction nodes get overwhelmed, or there's a power outage, or, disk dies, the underlying architecture can notice that and start rerouting traffic over here. Or a backhoe comes in and cuts your fiber and your entire data center goes down, like your local data center, it could transparently redirect that traffic off to Brookhaven or to another virtual facility. This is what is going to be the case in 10 or 15 years, because it's the only way to efficiently run a large-scale streaming readout facility. So this is some of the early work being done to build up that architecture to have redundant, self-healing networks. I think this is my last slide. Yeah. So, I've been talking about AI ML, and it's coming up everywhere. This is one of the things that was crystal clear coming from an experimental perspective within JLab. Not a whole lot of AI ML going on here. Of course, I'm aware of it because I like computers and been paying attention, but it is everywhere. The toolkit is super powerful. Reconstruction, like I've been talking about, tracking, cluster vertex finding, anomaly detection, all of the things that we've been discussing. It is being used for detector design, how to optimize a detector. EPIC is the EIC detector one, the first detector that's going to be built for the EIC that JLab is deeply involved in designing. And AI ML is being used to optimize that detector system. One of the big things here that I've already touched on is, there's a lot of concern about AI, about the black boxy nature of AI. And this is something that you, as young people in the field, need to be acutely aware of, is that, yes, it's a super powerful tool, but you're the only one with a brain. So you need to really think about how that system could fail and guard against those failures, in the context of the AIEC, the automated system that was trying to tune and maintain efficiency within one of the Hall D detectors, I think one of the GluX detectors, by adjusting the high voltage to maintain a constant efficiency. You don't want it saying all of a sudden that, oh, the efficiency went down, so I need to apply 4 kilovolts to the detector to get that efficiency back up. That would be bad. So you need to be aware of stuff like that and say, it's like, yeah, whatever happens, do not, you put in guardrails, right? So the system wants to steer over here. If danger is over here, that you as a human have identified as danger, but you never run the system over there, so the AI/ML can't know that that is danger because it's not been trained on it, you need to have a hard stop. So it'll come here, stop trying to make changes, and probably text somebody, send an email, send a warning, something like that, before it can do actual damage to the hardware or waste, 8 hours or 24 hours of very expensive beam time, things like that. Basically, be suspicious. All good scientists are really suspicious. So that's the big thing. The interpretability of the AI/ML, like I was talking about earlier, trying to learn what neurons, what part of the model is firing that is making a particular decision is a very active field of research. This makes me as an experimentalist feel a lot better because I'd like to have some insight into what my model is doing. And this research is explicitly devoted to trying to give some insight to this automatically generated parameterization, if you like, this AI/ML model. And I'm going to stop there.
So I was having a discussion with one of my senior grad students in our group who's about to graduate, Casey, I think you know him.
Mhm.
So we were just talking about containers. So as a grad student who is starting out his analysis, is it right now worth the effort to put in to keep all my stuff within or establish a container for all my stuff?
I mean, I would.
Okay.
So one of the things I'll tell you, I did everything that you guys are doing, right? I was a grad student once, and I'm assuming things haven't changed, but I got bored out of my skull doing analysis fairly regularly. So one of the things that I would do that has paid off a lot is if there was a thing that I had to do, 50 times and it would take me a day to do it, screw it. I'll learn how to write a script that'll do it automatic. And it might take me 2 days, but then I've at least got my task done and I have a new tool. And I was way more interested in the new tool than I probably was in a lot of cases, getting the task done, because I was pretty sure what the task result would be, but you have to prove it. So in the sense of containerization, just learning how to work with containers is a useful goal in and of itself. And that same is true of learning to use, Python. If you haven't used Python, number of the halls still use, raw root analysis and root scripts, right? Our data frames, it's a better way to go. So learn Python. If you haven't learned Python, learn Python. Python has got its problems. Personally, it's got its problems, but that is where the center of mass of the development community is. And you can do a lot of really good things really quickly within Python that you need to struggle to do effectively within the C++ root framework environment. So it's worthwhile, even if your professor wants you to write stuff, write root scripts. Pick a problem and do it within our data frames, just to learn how it is. And if it goes really, really well, you can run the bloody root script and you can run the Python thing and say, look, same result. This one was, 10 times faster. And teach your supervisors too. So containers, same deal. Go for it.
Okay, thank you.
Yeah. And if you run into problems, put in a help desk ticket, let us know. Because this on-ramp thing is something that I really want, that I, in my official job, really want to work on over the next several months. Been trying to gather the resources, but the more people that are interested in it, the more incentive there is for to allocate the resources to build these on-ramps.
And I like very much the teach your supervisor bit. I would appreciate it myself. So I have a question.
Yeah.
About this Phasma.
Yeah.
How much is it just a fast simulation of my code, and how much? So how should I think about it? It looks like a trick.
It does.
Run it. Okay, it is.
Well, so I can only say how I think about it. And I think about it as an automated parameterization. So it's a fit, fundamentally, in my mind. think of it as maybe a phenomenological model. If you had direct insight into what, the model did, like how it was doing its parameterization, then it would be even more interesting, because then you could probably assign certain portions of the model to, in the case of nuclear physics, like concepts of an electron or a particle or a field or something like that. And you could watch how the model has connecting those things together in order to generate the correct physics output, right? Based on a set of inputs. We can't do that yet, but that is being developed, is trying to figure out what portions of the model of the neural network, how are they communicating, how are they interacting in order to get from the input to the output, because that hopefully maybe will give you some insight into a more effective model for whatever it is that that framework is trying to simulate or represent or model. Does that answer your question?
Well, partly, but maybe
Partly.
I talk to you later on. I have a very, very old code. I do PDF fittings. And we have code starting in Photon 66 that there are blocks, all caps.
Yeah.
Over there, and then I
white
put in
space is very
Photon 90 bits, and then it's all a mess. So at this point in time, I'm even just looking at doing something else with it, but I don't have that time. I don't have students even to do that, so I cannot I'm really stuck. But one possibility might be, and sometimes it's just long to do things. It takes time to calculate. If I want to do a little more precise calculations, that takes longer time. So we're thinking, how much can I think about what you said as doing a fast simulation to explore the possibility. It cannot be as accurate as mine, because you are the AI is learning my code, so that there will be some uncertainty there. I don't know, but then maybe I can do super fast understanding where I should go, and then I can go there with my code, something like that.
Yeah. Well, so this, I think, is one of the explicit use cases, like design goals for this program. So, contact Nathan, Dave, or Sissy rather, and see. I don't know if how mature their framework is, if it's something that they can hand over and let you just play with, or if it's something that they have to kind of, hand roll a little bit and fire off themselves and then let you know. But I think what you describe is exactly one of the goals of this system.
Okay.
And one of the things to keep in mind, and this is true of AI ML in general, is I find a lot of people, my colleagues of my age and younger and older, are pretty skeptical of AI ML because, you don't know what it's doing, which is sort of true. It's something that's being worked on. And certainly I came from that field. Like I say, I grew up as a scientist, and I'm very suspicious. So suspicion's good. Paranoia is good, because it turns out the world is trying to get you when it comes to science and trying to figure out what's really going on. But one of the facts is that another aphorism that I'm very fond of is that, perfect is the enemy of good enough. And this is true of all of your analyses. When you're trying to do fits, you're trying to bound your parameterizations, you're trying to bound your systematic uncertainties. You can spend your life trying to get it perfect. Perfect is not your goal. Good enough is your goal. And good enough is, you need to be able to say that, yeah, this is, the range of applicability. And if I operate within this range, I believe the output within this range. Ideally, the uncertainties there would be zero, but in practice, they never, ever are. And if they ever are, you fooled yourself, because they never are. So with AI ML, right, a lot of these processes here and these things going on can be done in conventional methods, conventional techniques, training or tuning a detector system or things like that. Perfection isn't your goal. It just has to be, ideally, at least as good or better than whatever it is you're using before. And as you may, when you think about it, that is often a pretty low bar. So if you think about it that way, it may make you feel better about using some of these tools within all of the constraints, and you have to stay paranoid with it, that I've mentioned.
Last chance, Friday.
Yeah. All right. Thank you.